All right, folks, so I wanted to take some time here in this video to go through the test practice, which has been finally posted for your viewing pleasure on that BVHS AP Physics website. I apologize for the excessive clicking. I want to get back to Greg. So I'm just going to kind of talk through the reasoning behind a lot of these problems. I'm not going to do any of the actual math. You can do that on your own, but I'm going to talk about how to set up these problems. So for this first one, we've got 4 identical objects that are moving to the left at the same speed and have net forces. The first one says to identify all the objects that are having a decrease in kinetic energy. Well, if we take a look at the work done, or the net work, that is equal to a change in kinetic energy. So as long as I have a negative work being done by that force, that results in a loss or a decrease of kinetic energy. The only ones that have that are letters A and D. They both have forces that are at least somewhat in the opposite direction of the direction of motion. All the objects that are both increasing in kinetic energy and changing direction, again, we need a force that is in the same direction, at least somewhat, as the direction of the motion, but we also need it to not just be in the direction of motion. Letter C, that force and the direction of the motion are parallel to each other. They have a 0-degree angle between them, which means that it's just going to accelerate by speeding up, whereas letter B has a positive work that is at an angle. It will have some change in direction to it. And if the net forces acting are all equal, rank them from greatest positive to greatest negative. Greatest positive will be C. All of that force is being used to have a positive work being done. There's no angle there, so it's times 1. B is next, then D, and then A has a the most negative work possible done by A. On to number 2. This is just a problem where we're dealing with conservation of energy. Up here we've got a couple of different values that it gives. And remember that as long as there's no friction, it says it's a frictionless roller coaster, so I circled that. Anywhere in this roller coaster, we have the exact same total mechanical energy, that potential plus kinetic that we start with. So for the first one, if the roller coaster leaves point A at 8 meters per second, we've got some potential and kinetic energy. At point B, we will also have some different kinetic and potential energy. So mgh plus 1/2 mv squared for the initial points equals mgh plus 1/2 mv squared for the final. Then it mentions what speed will it have at point C. Well, we get to use the same starting values that we already did. It will still have that same total amount of energy. There's nothing that's going to change that. No friction, no outside forces, no non-conservative forces. So that value then still equals 1/2 mv squared plus mgh, now just for at point C. And letter C for this problem brings in a little bit of circular motion for that loop-the-loop. Now that you solved for the speed at the top of that loop in letter A, you can plug that in for your velocity in net force equals mv squared over r. So I put a B in there for the speed at position B. Number 3, power required to lift a 4-kilogram mass upwards at a constant speed. I did the change in energy over time. My change in kinetic energy is 0, so my change in energy is just the potential energy change. Here now it gives a change in actual speed, but it does not have a change in potential. So A and B are kind of the opposite problems. They're still based on that change in energy over time, but one has a change in kinetic, one has a change in potential. And for letter C, we've got a 16-kilogram mass pushed across a horizontal surface with coefficient of friction. What power must be supplied to move the box at a constant speed? So for this one, I started by saying, all right, the applied force, the force that I'm pushing with, has to be equal to my force of friction. I know that because it's moving at a constant speed. That means no acceleration. That means no net force. So those two must be equal. My force of friction is kinetic friction, which means it's mu sub s, not mu sub k. I don't know why. I'm sorry, it's mu sub k, not mu sub x. S. So mu sub k times the normal force. That normal force is mg because it's on a horizontal surface. It's not accelerating down or up into the ground or off of the ground at all. So because of that, mg is my normal force. I plug that all in for the force and the power equals force times velocity equation. and then I can solve since I have all of these variables known to me. Next up, we've got this swinging mass at various different points. First question, at which point does the mass have the greatest kinetic energy? That would be point D, that lowest point in its swing. We've converted all of our potential into kinetic at that point. The greatest potential energy would both be at A and G. They are both at the same height, and they are the highest height that we have. Which position does have the greatest mechanical energy? They're all the same. There's nothing in there about any friction. In fact, it says assume no friction. So if we assume that there's no friction, then we have no work done by non-conservative forces. There's nothing to change our total energy. And at which of the following positional changes has the greatest increase in kinetic energy? To get the greatest increase, I need the biggest negative change in potential energy. So I need the biggest height change, but that height change has to be downward. So D to G is out because that is an upward change. That means I would actually be slowing down or decreasing my kinetic energy. And A to B is actually the greatest height change. If you take a look there, assuming that they're all 30 degrees, the higher up you are, that 30 degrees at the top is going to be more downward than as you sort of swing through that, that arc. So A to B is the correct answer there. At point D, the mass is moving there. How high above point D is point A? Again, just like the last problem with the roller coaster, our beginning total energy equals our final total energy, 1/2 mv squared at point D, mgh at point A. Plug in and solve. Work done by the elevator now to lift this man, force times distance times cosine of theta. The force here is going to be 850. As the man is 850 newtons downward, that's his weight, and he's moving at a constant speed. That means, again, our net force has to be 0, so plug that in and solve with the 21 meters. Power generated, that just is the work that we just solved for, divided by the 14.2. And the network, remember that network is a change in kinetic energy because there was a constant velocity. That means there was no change in kinetic energy, so the network is 0. Scrolling down again. If we have a not frictionless inclined plane, the work done by gravity to pull down the block to the bottom of the incline, work done by gravity is just negative mgh. Because that height change was a negative change, that would be positive work done by gravity. Work done by non-conservative forces, remember that work done by non-conservative forces is the same as a change in energy. So I'm going to figure out what my final kinetic energy is, right? It doesn't have any potential energy at the end. So my total energy is just this kinetic. And at the beginning, my total energy is just this potential energy. So final minus initial here to get that work done by non-conservative forces. And the net work done on the block, again, change in kinetic energy is the same as net work, so I can just look at the kinetic energy change. We started with no speed. It started from rest, it said that in the problem, and it ended at some speed, that 6.4 meters per second at the end. The block does weigh 30 newtons, which means that is a 3 kilogram block. Make sure you can differentiate between weight and mass. Mass held at equilibrium with this spring. It's gently lowered again at rest. I know we did a problem that was similar to this in class. I think the springs were on the other side of the object though. So the kinetic energy, because it started at rest and ended at rest, it is the exact same. By lowering this object, we're changing the height. We're making the height less, which means that the gravitational potential energy is lower, but the elastic potential energy is increased. It got stretched out, which means that it has been displaced from this so-called equilibrium point. And if we calculate the total change in energy, we have a final that if we call this height 0, at the end, we just have some potential spring energy, And then at the beginning, if we call this the equilibrium position, we just have some gravitational potential energy. And that x and the height is actually the exact same value, so you could use that exact same, well, what's the word I'm looking for? The exact same variable there. That for both of those, that would be the 0.2 meters. Total energy at point B would be some height plus some speed. But let's see if, and it does give us enough information there, right? It gives us the speed, it gives us the height, both at point B. And it's this problem really should be saying what's the mechanical energy needed at point B to make it across the gap. Or I could ask you about at point A, because they're going to be the same. That energy is conserved. There's no friction there. So if we take this total energy here, at the beginning, that has to equal just 1/2 kx squared. So we know the x, that distance that it has been compressed. Now we're looking for the spring constant of the spring to make all of that fit. And as it goes across the gap, it is both kinetic and potential. Now, a lot of people say, well, it's at the highest point. Shouldn't that just be potential? But remember, this block is still moving sideways as it's crossing this gap. So it still has to have some speed at the top, at its highest point. It's directed horizontally instead of vertically, but it is still there. So it is both potential and kinetic. It's moving and it's above ground. This is an old AP question. Two identical blocks are released from the top of their slides at the exact same time. Which block, if either, lands farther from its table? They both land at the exact same distance. Both of them go through the same change in height, which means they both go through the same change in potential energy, which means that at the bottom, as they leave the table, they both have the same kinetic energy and therefore speed. So if they both have the exact same speed, table has the same height, that means they will fall at the same rate, and with the same speed, they will go the same distance in that exact same amount of time. Which block, if either, hits the floor first? It's actually block 1. A lot of people misread that question. They say, well, they both take the same time to go from the top of the table to the bottom of the table, and I would say that is true, but they don't take the same amount of time to go down their respective ramps. Block 1 speeds up a lot quicker. It goes through that changing kinetic energy much more rapidly. Block 2 has this little bump there, and it takes a little bit longer for it to speed up. So block 1 gets to its top speed a lot quicker, and therefore it gets to the end of the table first. Its changing kinetic energy happens more rapidly. Graph of a force and distance for a spring. Force constant is going to, or the spring constant, sometimes called, it's the same thing, is the slope of that line. Just draw a line of best fit, and then the amount of work would be the integral there. If we graph the potential energy, and I didn't get the numbers in there, but I'm just drawing the shape. Remember that we have a parabolic shape. The green is going to be the potential energy. At zero displacement, you have no potential energy. That x is 0. And it has this parabolic shape. And then if we sketch the kinetic energy and total energy of the mass spring system, it is a inverted parabola that should peak at the same point. I drew it rather quickly, and then the total mechanical energy should be a flat line at some height. Again, I did not do that calculation of where that line should be. You can do that on your own. 1/2 k x squared at its maximum displacement of 0.6 meters. To the next one. Now we've just got a net force distance. How much kinetic energy change? Well, that is the net work, which is the net force times the distance. So for this graph, that would be the integral. So take the integral of that graph. And then what speed will it have? Well, if we know the initial speed and we just solve for that change in kinetic energy, we can then find that final speed by plugging in.
Please report to the front office. Darren Vodder, please report to the front office.
If we take a look at this graph, first we want to identify each of the following energies based on what shape they've been used. Because we have a situation where we don't have any change in change in total mechanical energy. There's no non-conservative forces. It's just gravity. That means that this constant line has to be the mechanical energy, that red square. And we start with potential energy because we're at the top of a building, but then it ends up on the ground, indicating to me that this blue dot is going to be our potential energy. We start with some and end with none. And for kinetic energy, we still do start with some. So we have this sort of upshifted graph because it was thrown horizontally. We gave it some initial velocity. But then it ends up with all of the energy being just kinetic energy. To find the mass of the ball, we could pick any point and do MGH. I would personally pick the beginning because I know it's 20 meters and I know it's 800 joules, so I can plug in there. And then at what speed was the ball thrown? Again, we can take this first point now that we know the mass, and that energy is 200 as the joules of kinetic energy that we start with. Similar type of graph, but now we've got this sort of sloping piece to the total mechanical energy. And in order to find how much work was done by air resistance, well, air resistance is a non-conservative force, so that's the change in total energy. I would take this final value of 800 minus 1,000. I lost 200 joules of energy to air resistance. That's how much work was done. Terminal velocity occurs when the upwards force of air resistance is balanced by the downwards force of gravity. When we have those balanced forces, that means we are no longer accelerating. We're no longer changing our velocity, which means that our kinetic energy also would not be changing. If you take a look at this graph, to me, it still looks like we're changing our kinetic energy. We haven't sort of leveled that out yet. And what net work was done on the object during the fall. Again, net work is change in kinetic energy. I think that's the fourth, maybe third or fourth, maybe fifth time that's shown up. That idea that kinetic energy, the change in kinetic energy is the same as the net work. So here again, 800 minus 200, so 600 joules of work done total. And we have some doubling kind of problems. If we double the kinetic energy of, if we double the mass and the speed, it would be, let's see, 2 squared is 4 times 2 is 8. I put this 1 here where the 1/2 is. That is the most commonly done wrong piece of these problems. That 1/2 didn't change from beginning to end. It didn't change from the car driving at 15 meters per second to doubling it. Now, because I gave you actual values, I could, you could go through and do all of the calculations. You could say that the speed is now 15 and the mass is now 2,000 and actually get those two numbers and compare them, but this is a little bit easier. By what factor will the stopping distance of the car change if the speed is cut in half? So if you are going half as fast, that means you have a fourth of the kinetic energy, which means that you have a fourth of the work that you have to do. And assuming that the force applied by the brakes is constant, that means that the distance would be a fourth as much in order to stop the car, because work is a change in energy. The car accelerates up. How much power did the motor have to do? Figure out that change in energy and divide it by the 7.8. Car's later moving, goes up a hill towards a stop sign. Total energy converted by heat. Look at your final energy. You have some vertical piece, some potential energy, and it is stopped, so it has no kinetic. So this is just MGH at the end, and we've just got 1/2 mv squared at the beginning. Couple more here. We've got a set of 3 tracks, which has the greatest change in kinetic energy. They're all the same because they all go through the same change in height, which means they all lose the same potential energy, which means they all gain the same kinetic energy. And which car reaches the bottom of the track in the shortest amount of time? That is A. It's the most direct route. It speeds up the fastest. B has this piece where it's going relatively slow and then it starts speeding up again. Down here at the bottom, if we drop an object off a roof versus throw an object off a roof, which object would have the greatest change in kinetic energy? Again, just like before, they both have the exact same change in height, so they have the same change in kinetic energy. but which has the greatest mechanical energy is actually B, the one thrown sideways. It had some kinetic energy also to start because we gave it some initial speed to the right. So we get to add that to the MGH that it had to start with. So it has more. Which reaches the ground at first. They both hit at the same time. That horizontal component doesn't affect the vertical fall rate of that ball. And that takes care of it. So hopefully that is helpful to you. If you're wanting to take the test tomorrow, being Friday, that is great. Or if you want to defer until Monday, that is also great. Hope this is helpful and enjoy the rest of your day.